forward. This looks a bit strained in that for the way I've drawn this, but if you take actually I should turn on my camera and show you this. I'll stop sharing. When you make a model, look at that. It isn't actually very strained at all. So what we're making here is like this ring system nicely folds around, and it's just between this guy in the blue and this guy in the blue. So it's relatively it's a nicely tethered reaction, and the cyclization, it's not a, because when you draw certain things on paper, it looks like it's oh, there's no way that would reach around, but in reality it's just like it's just almost like when you had some of those intramolecular Diels-Alder reactions. So if you make a model of it, it works out very beautifully. So this diagram here, where I've tried to draw this, is pretty accurate. So it's just not this bond across the top makes it look a bit strange. So if this attacks here, then this carbon is going to develop a positive charge, and then this double bond is going to attack that positive charge, which is going to leave a positive charge in the middle, and then the water comes in, and that's how you get this on the bridge, this hydroxy group there. So you've made all of the bonds of this, so here, two ring systems through this cationic cyclization. So it's a really neat reaction. So you generate a allylic carbocation, and then the triple bond attacks. And the other advantage of the triple bond is that it leaves the double bond for to be functionalized further. Plus, it's linear, which means that it's easy for the reaction to take place. There's not as much sterics associated with it. So this is basically the key step of the reaction. It's quite neat. Now, all we need to do to finish off the synthesis is basically, the steps to do is remove the hydroxy group, and we need to put a methyl group here, and we need to put a double bond here. So there's just 3 things left to do in the whole synthesis. All right, so the next step is the removal of that hydroxy group. Any ideas as to what's going on here? So zinc bromide, what is that? What is this? And then we've got sodium borohydride. Sodium cyanoborohydride. So we've got, I think this was a reducing agent too. So sodium cyanoborohydride, when it comes to being a hydride, is this a strong hydride or is this a weak hydride?
Weak.
Right. So this is one of the weakest ones. So it's a very weak hydride. In fact, it's used often to reduce imines, to make amines, so reductive amination, and you start to make the imine, you can start with an aldehyde and an amine. And the sodium cyanoborohydride doesn't actually reduce the aldehydes, so it is but it is enough to reduce an imine. So it's a very weak reducing agent. Okay, so that's good. Now, what about the zinc dibromide? What is that? If I threw you back in organic 1 and I said, okay, classify this species as something, you would say, oh, it's got to be a such and such because of such and such. I need to learn how to do the polling function of using Zoom. So is zinc dibromide a Lewis acid or is it a Lewis base?
A base, I think. I don't know.
So, okay, so to be a Lewis base, you need lone pairs that you can donate. That was a general definition. To be a Lewis acid, you needed an empty orbital to donate into, or a low energy empty orbital, or a polar bond to hydrogen. So because zinc's transition metal, we would typically classify these as a Lewis acid. And here we've got a Lewis base. Really what we need to make over here is a carbon-hydrogen bond, CH bond. So the source of the H is going to be the sodium, the hydride itself. Now, what is it actually attacking? So there's some speculation as to what's going on here, and I'll basically suggest it, and then you can tell me why this might be wrong. Okay, so Lewis base complexes with zinc. You end up with plus, and we could lose one of the bromines, it doesn't really matter there. But you generate a complex like this, and then this leaves because now it's got a positive charge and it can leave as OH, ZN, Br, something like this, and you end up with a carbocation. Bromide, the hydride comes in, and bingo bango, you've got your CH bond. Okay, now this seems like a reasonable potential mechanism. What part of it do you not like? And this might be because of the way I've drawn everything. Or do you just think this is wonderful? this is what they propose, and I don't think that it's not correct. What they need to, what you really need, it's interesting that there are other ways to to convert OH groups into carbon hydrogen, converting an OH bond into a a carbon oxygen bond into a carbon hydrogen bond. There's a number of ways to do it. The interesting thing about this, our starting material though, is that, and there's a way to do it through a radical mechanism. If you generated a radical here, there's ways it could fragment, which would ruin all of the stereochemistry. So, which could break some of the carbon-carbon bonds. So it's interesting that this was what was chosen. The thing which is interesting, which people think that it might not be this, is the fact that the carbon here, if it's a carbocation, it should be trigonal planar. So it should be flat. And it would have to be distorted a bit to do that. So, like, for example, it's very hard to produce carbocations on these types of carbons here because they can't get that flat. But anyway, I think that it's a reasonable mechanism for what it worked. So I'm gonna just erase all this stuff. So that's what's going on there. They converted the OH group into a carbon hydrogen. Now the last two steps are really fun. Okay, so go back to this. I will draw this out. Para-toluene sulfonic acid. Okay, so I just gave it away. This is an acid. Okay, so how does this mechanism work? So we go from a tetrasubstituted double bond to basically a disubstituted double bond. So this reaction is a isomerization, really, because all we're doing is we're changing the location of the double bond. So the first step will be what? And we've got a source, basically a source of H+.
Protonate the double bond.
Okay, and so we're going to make either, when we're protonating this double bond, you'll notice that you could have a positive charge here, and I'll just draw the loop like that. Or, sorry, this would be, or we could have the positive charge here. So this would be the product from A, and if the proton went on carbon B, it would be this one here. So, and then the next step, what's the last step once you've got the carbocation? What are we doing then? So we basically need to remove, if this has got, say, 3 protons here, we need to, the conjugate base of this, this would just basically come and grab one of those protons and you'd form your double bond. But it's interesting that you start with a tetrasubstituted double bond and you end up with a disubstituted double bond. And if we think about double bond, like which one's the most thermodynamically stable? Tetra are more than tri, which are more than di. So what's going on here that makes this reaction take place really quickly, half an hour at room temperature, and the yield's really, really good? So the two carbocation intermediates are both tri-substituted. Why do you think that we end up forming this we call these, whenever you got a double bond which is sticking out of a ring, we call these exocyclic. Why do we have an exocyclic double bond as opposed to an endocyclic, where it's part of the ring?
Sterics.
Yeah, this, if you think about, let me erase something here. If you think about, get my laser. This carbon here, this carbon should be flat. It should be sp2 and it should be flat. The way that we've drawn this, you can sort of see how this carbon here is nice and flat in this area. But this one, you've got carbons, this carbon's going up and this carbon's being sort of pulled up. So there's a certain amount of strain associated with this double bond. So if it gets protonated, and there's only one direction to get protonated, that's down, because these are both going up. You're releasing a lot of that sort of strain. So you generate this carbocation here, and then to remove protons, this proton on this ring is not aligned properly to make a double bond, because the proton here is sticking. If you've got, remember, if you're making this proton here would be sticking straight forward, and the pi system is going to be this proton can't be eclipsing. This proton's got to be the proton that's being removed to form a oh god, I'll have to erase everything. Just remember, if you've got a carbocation and you want to make a double bond, the proton that's being removed has to be lined up with that carbocation. It's got to be parallel to it. So these electrons have to fall into that orbital. This proton here is totally in the wrong space. It would be this proton would be sort of horizontal, laying flat. So it's not, the orbitals are in the wrong direction. So it's got to be lined up. So that's why this one can't form a double bond. In fact, there's a rule about double bonds and ring systems like this. The rule is that you can't make double bonds there. Unfortunately, there's a number of different examples where, anyway, that's Brent's rule. You can't have a double bond like that on a bridgehead carbon. There's a couple instances where it does take place though, and we'll see that later on in the class, but anyway. All right, so it's a migration using an acid, and we end up with our double bond there. Good, okay. Now the next question is, so we're almost done. There's only 3 steps left. So that's good. We have seen in organic 2 this guy. I don't think we have seen the ruthenium ever before. But what does it remind us of? Ruthenium tetroxide. So there's a catalytic amount of ruthenium tetroxide, and the sodium peridate is the main oxidant. So we got a co-oxidant and we got the, so together the NaIO4 can reoxidize ruthenium to ruthenium 4 or ruthenium tetroxide. So this is basically, but we've seen something very similar to this in organic too, right? We would have used osmium tetroxide on a double bond to make a diol. And then we would have used NaIO4 to make actually there's another oxygen in here somewhere. And then this fragments, you would end up reducing the iodine and you end up with a, do we remember that? So another way of chopping alkenes in half is to use ozone. And this would, if you used ozone with this, we would make, on paper, we would make the same product. But if you don't have an ozone maker, one of the things to use would be osmium tetroxide to make the diol, and then NaIO4 to cleave that diol. Osmium tetroxide's really toxic, so there's lots of reasons why this wouldn't be used. Ruthenium's extremely expensive. So this is back in the 70s. So I guess using this was what they decided to do. So, but we're going to need this ketone to install the last group at this carbon here. So this is basically converting an alkene to a ketone. And there's a number of different, like ozone's one way to do it, or these routes here, but that's all very similar. And so this is so LDA, and we are making an enolate. So yeah, this is interesting. So there's two hydrogens here. And if you think of a carbonyl, what's the best way to do this? So if you're making an enolate, so here's our carbonyl. Carbon, oxygen, double bond. Carbon next door, so an alpha carbon. Carbon next door, alpha carbon. If you're going to generate the enolate, and I'll draw that over here. Oh, darn it. All of these pi orbitals have to be lined up together. So The same principle as applies as to what we did in the last section. So this proton, these electrons, if the p orbitals are like this, these electrons are basically lined up so they're parallel with the p orbitals, whereas the electron density here is perpendicular to it, so it's not like lined up. So if you can remove one proton and not the other, because one's gonna, these electrons are lined up to overlap. These electrons are horizontal, and so they're actually in the plane of the carbon oxygen sigma bond. So only this proton here can be removed. Don't have to worry about the one on the other side. And then once it's been removed, the ring goes up, there's only one direction which it can attack the methyl group, and that's from the opposite side. So that's why the methyl group is down, because this is up, this is up. There's only one way to go, which is down. So that's neat. So the proton which is being removed is electron. The electrons in the carbon hydrogen bond are lined up so the overlap is perfect to generate the enolate. And there's only one way that the electrophile can be attacked from, and that's from the opposite side of the large ring at the top. So you generate the one possible product. And then the very last step is just generating a double bond. And the fun part is they do this through some chemistry which we probably don't quite I don't think we've done this before, actually. Well, we certainly would have done the first step, but the second step, I don't know if we've done the second step. But one way of doing this reaction that's not included here is just to do the Wittig reaction, pH. So remember, this was phosphorus with a positive charge, carbon with a negative charge. pH3. And then these electrons would come in and attack. Now, the trouble is, like, someone might have tried this previously and it might not have worked. This group's quite big. So, and you need to make a four-membered ring when you're doing the Wittig reaction. So you'd have to have something like this. We remember that correctly. Phosphorus. And then it breaks apart. Those electrons go there, those electrons go there. So it might have been just too large. So they used a different route to make this reaction. So I guess we should go over this because this is the very last step. So what's going on in the first step? What is methyl lithium?
The nucleophile.
Again, it's a nucleophile, right? Okay, so carbon with the minus, delta plus, delta negative. Carbon comes in and attacks, and I'm guessing it's probably going to come from the bottom side. It's probably the least sterically crowded. So we would end up, once this thing gets I'll just draw a big loop there in the methyl group. Okay, now that's good. Let's erase some stuff. What would be the next step? what is thionyl chloride? What type of reagent is this? I'll just erase that just to save some space. If you had to, I'm going to leave that as a negative charge. Like you add your methyl lithium, and then your next. It doesn't. I suppose it doesn't really matter if it's an alcohol or if it's been deprotonated. But what is thionyl chloride? If you had to predict its reactivity, it's quite a reactive substance. You'll notice that it is attached to 3 fairly decent electronegative groups, which makes it quite a strong electrophile. So if this oxygen was to come in and attack, technically sulfur's got 2 more lone pairs there. What we're going to end up generating is, I'm going to erase this for the time being because it's too big. We would expect to make this Cl minus and this is CH3. I think in organic too, we use thionyl chloride to convert secondary and primary alcohols into chlorides. Did we not? So if you had a primary alcohol, which has now been attached with thionyl chloride, am I not remembering this correctly? This goes here and that goes there, and you can just change out a convert an alcohol to a chloride using thionyl chloride. Did we not do that ever? I'll take that as.
I don't remember.
Okay, well, yeah, it might have been one of those side reactions that we didn't talk about a whole lot. But here we've got this carbon here is actually technically is a tertiary carbon, right? So, and you've got pyridine here. So what's going on is we're effectively doing an elimination reaction where one of the protons is being picked off. I'll just draw one like this, where the base is picking off a proton here, and that's going there, and then that's leaving. So we've generated a relatively good, really relatively good leaving group. And it produces sulfur dioxide, which basically bubbles out of the reaction and makes the reverse reaction impossible. So this is basically, the way it's being used here is it's being used as a dehydrating agent. So we're effectively removing water from the molecule, converting the alcohol to the alkene. They could have used probably a mesylate or a tosylate and just done another elimination reaction. There's only these protons on the methyl group, which has been added from the methyl lithium, can be removed because the proton on this side isn't lined up properly. And yeah, so it's basically, that's the only possible reaction which can take place. On the other side, you've got a methyl group. so there's no protons on this carbon here. So yeah, there's only one way to do it. So yeah, but these, using thionyl chloride isn't probably the funnest thing to use. It's stinky and toxic and that sort of stuff. So there's other ways of doing this now, but it's one of the reagents that was used in the back in the day, I guess. So that's basically the synthesis. Overall, the yield was 21%, starting from this compound. It was 10 linear steps, so it wasn't, and the key step was that cationic olefination reaction, which made those two ring systems in one step. So that's really a really nice reaction. The rest of the reactions were fun in the sense that it got to remind us of some of our chemistry from years like organic 1 and 2. So that's the nice part. Some enolates, which is new stuff, some organic cuprates, some 1,4 addition, some 1,2 addition, some elimination reactions. There's a 1,4 or 1,2. This is the cationic cyclization. This is a new reaction we haven't seen before, which was interesting. Migration of a double bond, oxidative cleavage of a alkene using some reagents, which the ruthenium we certainly hadn't seen before. And then back to our some enolates, 1,2 addition, and then a dehydration. So it's a fun little synthesis. And there was some fun chemistry to talk about. So that's basically, so I'll put up the folder with the various syntheses in there, and in that folder I've basically divided the class into groups, and I'll do that sometime later on today to so everyone can sort of get started. And if you want to choose one of them and let me know, that would be good. And I think that's it. 2 of the papers come from research groups in Canada, which is nice. And a couple of the other ones are, I think they're basically all at American universities. One is from the same person who did when I did the Birch reduction paper, reduction one. One's from his research group too, so that's kind of fun. So trying to weave it all in. Now, what time is it? It is 1:30. Okay, so it's perfect time to end the class. Were there any questions?
Dr. Hill, could I talk to you for a minute after class?
Sure.
So our groups are going to be covering one step, or I can't quite remember how you were explaining it, or one paper. I can't.
Yeah, so there's one paper, and so each group will do one paper. It's the same synthesis, so everyone's going to get pretty bored of this molecule, but the approaches everybody uses is totally different, which is the fun stuff. So it's basically saying that there's more than one way to do something, which it's all about creativity and that sort of thing. So you can just do a little presentation, just sort of like what I did. And you don't need to explain every step in the detail that I did, because mainly what I was trying to do is teach class as well, right? So some of the synthesis will have like use protecting groups. This one didn't use any protecting groups at all. So when you start using protecting groups, you sort of double the amount of steps that a synthesis might have. So if something like that's going on, you can just say that this is a protection and this is a deprotection and that sort of stuff. But the next, on Tuesday, I'll do another synthesis, probably the prostaglandin synthesis. And as we go over these over and over again, you're going to basically get a good feel for what's going on and how to do it. Does that make sense?
Yep.
Okay.